Here in Chapter 14, we're going to study bearings. We have a few standard homework problems for you, 14.1, 14.9, 14.11. 14.18 will apply to Figure 12.3, which was used in homework problem 12-24. Word to the wise, if you didn't get full credit for 12.24 in the homework grading, then you probably should use the homework answer key for 12.24 in order to figure out what bearing you need. And then we do have an open-ended homework problem to go to the SKF website, which is, SKF is one of the premier manufacturers of bearings in the world, and find the spherical roller bearing that would be acceptable for bearing D of shaft 2 of the homework problem 12-35. We also have a very good video for you to watch, and that's on YouTube. That's all about how you assemble bearings into machines and gets into the video details of how a lot of the components work. In the picture here on the bottom, you do see all the different types of bearings that we're going to study in this class today. The most common bearing is called a ball bearing. In a ball bearing, the inner race is lightly press fit onto the rotating shaft. The outer race is typically press fit into a housing. And the balls in the ball bearing rotate in deep grooves cut into the inner and outer races. Large balls and races allow support of larger loads, or you can add a second row. This is then called a double row bearing. And you can see in the picture that there's about 8 balls. The number of balls is really related in these bearings to the diameter. The larger the diameter of the bearing, the more rotating balls you're going to have, and the more load that you can take. In a cylindrical roller bearing, you replace the spherical balls with cylindrical rollers, and you get a greater radial load capacity. And this allows you to have a smaller physical size of the bearing with the same load capacity. Theoretical line contact is shown between the roller and the race, and it deforms to a rectangular surface under load. The downside of using a cylindrical roller bearing, though, is that it has poor thrust load capability, and that's due to the load pushing on the side of the rollers. Now, a needle bearing is a cylindrical bearing with very small diameter cylinders. They're so small that in the smallest of the needle bearings, they really do look like needles. Needle bearings are commonly used in precision aerospace instruments, precision pumps, and in universal joints where space is at a premium. You may recall when we had our video about an auto repair with universal joints that bearing in that system was a needle bearing, and the technician in the system talked about having to place the needles in the bearing because they had fallen out. Now, in a tapered roller bearing, the rollers are tapered and they're not straight cylinders. And in this case, the tapered roller bearing is used as wheel bearings for vehicles and very heavy-duty machinery. Because the bearing is on an angle, you can accommodate both heavy, radial, and axial loads. In a spherical roller bearing, you have 2 rows of rollers, a common sphered outer ring raceway, and 2 inner ring raceways inclined at an angle to the bearing axis. And the center point of the sphere in the outer ring raceway is at the bearing axis. If you look inside the spherical bearing, you have rollers in the inner raceway, and the bearings are self-aligning, and they're insensitive to the misalignment of the shaft relative to the housing. And as such, you can accommodate heavy radial and axial loads. Now, in a thrust bearing, you have raceways machined into the faces of the mating rings. Thrust loads, meaning parallel to the bearing axis, are supported, but radial loads and moments are not. Cages or retainers are used to maintain the uniform roller loading and the spacing, and the key issue here is that you only use a thrust bearing to support the thrust load. Now in a pillow block, you have bearings pre-assembled inside housing, which in turn mounts to a machine. And you even have a grease fitting on the outside of the pillow block so that you can add grease periodically without having to take the bearing out. And they're useful in very large machines with suitable space to mount the housing. If you want to see a pillow block bearing, go to the gym. They're commonly used in gym equipment. This chart out of our textbook, Table 14-2, shows the bearing materials that are commonly used. Balls, rollers, and races are usually made from SAE 52-100 tool steel, which has a Rockwell hardness of between 58 and 65. When you get into the ceramic bearings, it's because you have to have the bearing hold up to very high temperature. For most applications, the bearings are using either the bearing steel or stainless steel. You don't want to have a plastic bearing unless your loads are extremely small, your temperatures are very low, and you're cost constrained. Here's a comparison in Table 14-1 of different bearing types. We see that the single roll deep groove ball has good radial load, fair thrust load capacity, fair misalignment capability. Not shown in the chart is that it's the most cost-effective of all your bearings. If you want to have excellent radial load capacity, excellent or at least fair to good thrust load capacity, and excellent misalignment capacity, you can use a spherical roller bearing, but you're going to pay. And the other bearings fall somewhere in between. You do need to lubricate your bearings. Typically you have a low friction film between the rollers and the races. You can use clean mineral oils, although the heavier loads require much higher viscosities. Most bearings are what they call closed lubrication housings. Bearings are press fit onto shafts with light interference fits, typically FN2 or FN3 as we defined in Chapter 13. You do need some axial preloading on some thrust bearings. Some bearings are sold with a permanent seal with no lubrication needed for the life of the bearing. And the bearing specs do include the max RPM for the rated load. In this chart we show you a little bit the picture from the SKF website of how you actually assemble a bearing into a shaft and into a housing. The first thing you do is you have this fitting tool that pushes the bearing into the housing. And this application, the shaft shoulder diameter sits against the bearing inner race, and the shaft bore diameter is a light press fit inside the bearing inner race. The housing makes a tight clearance fit with the outer diameter of the boring, typically RC3 to RC4. You can retain a bearing from axial motion if you use retaining rings, but if you go with a slightly tighter fit between the bearing and the housing, you won't even need to do that. We have to calculate a bearing load versus the life. The basic static load rating C sub 0 is the load the bearing can withstand without permanent deformation. And the basic dynamic load rating is the load at which 90% of a sample of bearings will support the rated load P1 after 1,000,000 shaft revolutions, given the term L1. And we use the formula 14-1 to find the life L2 of a bearing running at a different load, where L2 over L1 equals P1 over P2 to the kth power, K equals 3 for ball bearings and 3.33 for roller bearings. And the general idea here in this formula is that if you want to run a shaft at a higher load than the rated load, you're not going to get 1,000,000 shaft revolutions. You're going to calculate a smaller number of revolutions, L2, using this formula. P1 is the rated load and P2 is the higher load that you want to run at. So here's a little sample calculation, example 4 MEC410 in the book for calculating the expected life of a bearing. P1 is 7,050 pounds. That's what's called the basic dynamic load rating, also given the symbol C. And the design load is 3,500 pounds, L1 being 1,000,000 revolutions, K is 3 because this is a ball bearing. And you would assume right away you're going to be able to get more life out of it because you're running it at a lower load than it's rated for. And when you go through the calculation at the bottom, yes indeed, you do find you get 8.17 times 10 to the 6 revolutions, which is roughly a factor of 8 times what you were able to get if you ran it at the rated load. We do have table 14-3 in our book to select ball bearings. And in this table, they give you the bearing number on the left side of the column, which is standard for all bearings around the world, which is kind of nice, so you can comparison shop. The bearings of the world have a millimeter bore diameter as a standard, and the inch bore diameter, meaning the inner diameter of the bearing where the shaft goes, is always going to be a 4-digit fractional number, imperial units. And in these bearings, they give you the width, they give you the outside diameter, they tell you what the dynamic load rating is, and they also give you the static load. They tell you what the maximum fillet radius that you can have shaft and still press fit the bearing on the shaft. And you can see those are very small numbers, and that's why we used KT equal 2.5 for the very small fillet radius where the bearings were press fit. They give you a minimum shaft shoulder diameter, which is the larger diameter pushing against the inner race of the bearing. They tell you what the maximum housing shoulder diameter too, and they even give you the mass of the bearing, so that saves you the trouble of not having to weigh it when you want to figure out what the mass is of your entire transmission. Let's take a look at the bottom of this chart so we can make sure you have a good mental model of what these dimensions mean. Here we're showing a step shaft where the bearing is press fit. The bore diameter D of the shaft goes to the inner diameter of the radius. The maximum fillet radius is 2.5. That's where the small diameter meets the large diameter. And the shaft diameter must be greater than the minimum shoulder diameter. That's the shaft diameter on the right, because you do need that shaft to be pushing on the inner race of the bearing, as shown on the lower right side here. That shaft shoulder has to rest on the rotating inner bearing race. Now the outside bearing diameter gets pressed into the housing, and these ball bearings usually have a recessed roller cover to hold the lubrication in, and that roller cover is slightly below the level of the inner and outer races. In bearing design life, the design life LD is found just by rearranging the terms in equation 14-1. L sub D equals C over PD to the K times 10 to the 6th. The basic dynamic load rating can be found by rearranging terms again using simple algebra. We give the dynamic load rating the character C. And L sub D can be stated in terms of the RPM and the hours of operation H, where L sub D, the design life, is equal to the hours of operation times the RPM times 60 minutes per hour. The bearing design life in hours for different types of machines is shown in table 14-4. Here you have design lives for basic appliances and medical apparatus being only 1,000 to 2,000 hours because they're not used very much. But when you get critical equipment in continuous 24 operation, like in a power plant or in a drive mechanism for a ship, you can actually require a design life of being 100 to 200,000 hours. And here's just a quick example 14-2 for how to calculate the dynamic load rating of a bearing. In this case, we have a radial load of 650 pounds and the shaft is rotating 600 RPM. We select a design life of 30,000 hours from table 14-4 and calculate L sub d and get 1.0 times 10 to the 9th revolutions. And then we use equation 14-3 and we calculate C, the dynamic load rating, and we get 6,670 pounds. And when we go back to table 14-3 and look for a bearing, we need to find a bearing that has a minimum of 6,670 pounds, preferably just a little bit more to make sure you've got a small safety factor. Here's example 14-3 for selecting a bearing for radial loads. Now, in this example, we have a pure radial load, and the inner race is to be pressed onto the shaft and rotate with it. And even though we have the factor P equals VR, the rotation factor being V, the rotation factor in this case is a value of 1 if the inner race of the bearing rotates, which is usually the case. You can actually design a system where the outer race rotates, but generally that's not too common in application. And if you look at this situation, it's basically the same data used in problem 14-2, and so the dynamic load rating is the same. It's 6,670 pounds. And when we go to look at table 14-3, we don't really have any information in this problem as to the minimum shaft diameter. So the only thing you can really do is look on the chart and find a bearing with a larger load rating than the 6670, and you just take the one that's just slightly above it. But you'll see that when we get into the next bunch of slides, that you do have to take the minimum shaft diameter into specification, because it's possible that based on the minimum shaft diameter, you're going to have to go with a bearing with a larger bore diameter and go to a certain degree over design the dynamic load rating. Oliver has his own way of learning about our material. He doesn't read the book. What Oliver does is he snips things. Gears, earrings, springs, shafts, fasteners, and frames. That's how Oliver learns. He doesn't read. The rest of us have to read the book. Oliver knows parts from sniffing. Oliver, yeah, gears. He's learning gears. Good job. But Oliver, your homework's late. That was 6 chapters ago. Now, Oliver was just sniffing earrings. But Oliver, my friend, that's not this week's chapter. That's chapter 11. We've already done that one. Oliver, those are shafts. That's chapter 12. We did that already. Oliver likes springs. He loves springs. Oliver, don't you, little kitty? But the problem, Oliver, is springs are in chapter 18 and we're not up to that yet. Oliver, little kitty, those are the fasteners. That's chapter 19. Come on, little kitty. You gotta read your material. Oliver, those are frames. We're not up to that yet. Oliver, good job, little kitty. You found the bearing. And the bearing has a housing. And it goes in the housing. Just like that. Now, as you know, Oliver doesn't come to class. But if he did, he'd be a good kitty and sit near the front. I'm just not sure if Oliver would get too much out of the class. Here's a step-by-step procedure to select the ball bearing for a shaft where the minimum shaft diameter has already been calculated. The first step is to find the bearing from table 14-3 or a website that has a slightly higher dynamic load rating than what you've calculated for the bearing. You also have to make sure that the static load rating on the bearing is slightly higher than the resultant load calculated at the bearing per your shaft design, but usually this isn't a problem. The next step is you have to make sure that the bore diameter D of the bearing is larger than the minimum shaft diameter at the bearing location. If D is too small, you select a bearing with the next larger bore diameter that has the closest dynamic load rating to C sub D of the first bearing, and you check if D is greater than the minimum shaft diameter. Once you select a bearing, you have to adjust the shaft diameter upwards to meet the FN2 or FN3 fit with the bearing bore diameter. This will be slightly greater, maybe 1/1000th to 2/1000ths, but you have to consult the bearing manufacturer's suggestion, or you have to calculate FN2, FN3 on your own and fit it with the bare boring diameter. Then you have to make sure the adjacent shaft diameter is greater than the minimum shaft shoulder diameter, but not large enough to hit the stationary outer diameter of the bearing. Then you may or may not have to resize the adjacent shaft diameter accordingly. And last, you size the inner diameter of the pillow block or other bearing housing around the outer diameter of the bearing. Let's go through a specific example of how to do this. Suppose that the resultant load on a bearing is 600 pounds, the dynamic load is calculated to be 1500 pounds, the minimum shaft diameter is 0.505 inches, and the adjacent shaft diameter to the left of the minimum shaft diameter is 0.725 inches. So when we look at table 14-3, our first thought is to try bearing 6201. This has a static load CO of 697 pounds, which is greater than 600. It has a dynamic load rating of 1,549 pounds, which is greater than the 1,500 pounds you need. It has a bore diameter of 0.4724 and a minimum shaft shoulder diameter S of 0.63. The first thing you notice is that the basic load ratings are okay, but that the bore diameter for the bearing of 0.4724 inches is less than the 0.505 minimum shaft diameter. So now we have to try another bearing. Let's try 6202. This one has a dynamic load rating of 1754 and a static load rating of 843, well above what we need. And in this case, the bore diameter is 0.5906, which is greater than the 0.505 minimum shaft diameter. But it also has a minimum shaft shoulder diameter, and that's for the adjacent shaft, of 0.748 inches. And the maximum housing shoulder diameter you can use is 1.220. That's also for the adjacent shaft. You also note that it has a maximum fillet radius of 0.0024, and that's connecting the small to the larger adjacent diameter on your shaft. And that's the reason why KT is going to be 2.5 at that location, because you have to have such a small fillet radius. So our next plan is to adjust the minimum shaft diameter upwards to 0.5907 inches, which is the interference fit we get with the bore diameter D when we look at table 515-5 in our textbook. But now we got our next problem. S, which was the minimum shaft shoulder diameter, is equal to 0.748 inches, which is 19.1 millimeters, and that's greater than the 0.725 inches for the adjacent shaft diameter. And what I'm doing in this photo here at the bottom is I pick the bearing 6202 dimensions off the SKF website, just to show you that the numbers that we have in our textbook are extremely close, but there is very, very minor variance from bearing manufacturer to manufacturer. In this case, Our textbook said go with 19.1 millimeters, and in fact, if you look at the chart on the lower right side for what SKF calls D sub A, they're saying that it should be 19.2 millimeters, but that's really not very much. So we change our adjacent shaft diameter to the minimum, let's call it 0.750. We make sure that that fillet radius is less than or equal to 0.024 inches. And we do know that we can't exceed the adjacent shaft diameter of 1.2 inches, which happens to be 30.5 millimeters. In this case, the bearing dimension, large D2 in the lower left-hand corner, is exactly sized to that 30.5 millimeters. When they talk about the abutment dimensions, they call it capital D sub A of 31.3 millimeters. Again, there is a small difference, but you really don't want that adjacent shaft diameter to get anywhere close, because if it does, what's going to happen is that shaft diameter will hit a stationary part of your bearing. And if that happens, you'll have a rotating shaft hitting a stationary segment way on the outside of the bearing, and you're either going to wear down your shaft, hear a very loud squeaking noise, bring the whole system to a complete halt, or some combination of all that three. So you really don't want to do that. Now we'll go over how to select a bearing to handle both radial and thrust loads. And to do that, we have to come up with an equivalent load to use in our calculations that handles both the radial and thrust loads. And that equation is P equal the equivalent load equals VXR plus YT, where V is the rotation factor that we had a few slides ago, R is the applied radial load, T is the applied thrust load, X equals a radial factor, and Y is a thrust factor. And we have a table 14-5 in our book to find values for X and Y for when E, which is a factor here in this table, is greater than T divided by R. Now the thing you have to be careful about in this table we have in our book is that it's only applied for one factor X of 0.56 for all values of Y. When you actually go shopping for a bearing of this type online, you will find that there is a much larger amount of information because there's a lot more values of X, the radial factor, than just 0.56. So the first thing we do is solve for the equivalent load rating P, and then we look for a bearing that has at least the load rating of P. So here's example 14-4 for how to do that. In this case, we want to select a single roll deep groove ball bearing from table 14-3 to carry a radial load of 1,850 pounds and a thrust load T of 675 pounds. And that could happen from a scenario where you had a bevel gear on the shaft which was supplying that radial and thrust load. Now the shaft is to rotate at 1150 RPM, and it has a design life of 20,000 hours. And the minimum acceptable diameter for the shaft is 3.10 inches. So let's go through this step-by-step procedure. The first thing you have to do is assume a value of Y from table 14-5. And you're not sure where you're operating on this table. And that's kind of the problem with this iterative types of problems, is that you generally have to go through it a couple of times. And that's why they're telling you to start with Y equal 1.5, because it's roughly in the middle of 1 and 2.3, which is the max-min Y values on this chart. The chart only applies for X equals 0.56, so we can compute a preliminary value of P, which is equal to VXR plus YT, and if you pump in all the numbers, you'll find that the preliminary value of P is 2,049 pounds. We then compute the required basic dynamic load rating C from equation 14-3 using P equal 2,049 pounds. Now we keep moving along and we calculate that L sub D, which is the life of the bearing in revolutions. We take our 20,000 hours, we multiply by 1150 RPM and by 60 minutes per hour, and we get 1.38 times 10 to the 9th revolutions. And then we calculate C, the dynamic load rating, and we sub in the values. PD was 2,049, calculated on the previous slide. LD is calculated as 1.38 times 10 to the 9th. Divide out by 10 to the 6th and take that value in parentheses and take it to the 1/3 power because K equals 3 because the problem said that we're going to select a ball bearing. And we get 22,812 pounds. Now let's move on to step 4. We select a candidate bearing from table 14.3 having a value of the dynamic load rating of C at least equal to the required value. And we can do that because C was equal to 22,812 pounds. And you notice here that bearing number 6316 has a dynamic load rating, a bigger number of 27,878 pounds. It also has a bore diameter of 3.496 inches, which is slightly greater than the 3.1 inches for the minimum acceptable diameter. Therefore, we can use bearing number 6316. Now we have to go to step 6. We have to compute T divided by C sub O, which was in our table 14.5. The C sub O value was 675 pounds. The 19,447 was the static load rating of the bearing, and we get 0.0347. And now we can use our table to interpolate and get a value for E. Notice that T divided by C sub 0 that we got, 0.0347, is in between the numbers on the chart of 0.028 and 0.056, and so therefore E is approximately 0.25. Now we move on to step 8. In step 8, T/R is greater than E because T was 675 pounds for the thrust load, and R was 1,850 pounds. And T divided by R is 0.365, which is greater than E, which was 0.25. So we can do another interpolation and find that Y equals 1.78, which is on this chart in between 1.71 and 1.99. Now we go to step 9. If the new value of Y is different from that assumed in step 1, we have to repeat the process. So in step 8, we calculated T over C sub 0 of 0.0347. In step 9, we recompute the value of P using the updated value of Y, which in this case is 1.78 as opposed to the 1.5 that we guessed earlier. So now we see that P equals 2,238, and recalculating C, we get 24,910. But these values are still acceptable for the 6316 bearing because the 24,910 is less than the 27,878 dynamic load rating for the bearing. Therefore, we're done. And if this were not the case, you would have to go back and specify a different bearing from table 14-3, run through your calculation one more time, and made sure that the revised bearing did meet the requirements of your problem.